Good day, everyone. I'm Theon Cruz, a fifth-year student taking up BS Chemistry and Material Science Engineering. I'm here to talk a little about graphene biosensors. So, graphene, one of the major discoveries in material science that many scientists are talking about nowadays. This nanomaterial is a single layer of pure carbon atoms arranged in a hexagonal or honeycomb lattice structure, or in chemistry is continuously sp2 hybridized. It was discovered in 2002 by Andrei Geim and Konstantin Novoselov at the University of Manchester by using sticky tape to thoroughly peel off layers of graphite until they got it into an atom thick. They tested its properties and found out that it had surprisingly superior electrical, thermal, and mechanical abilities. And through research and development, scientists found several uses for graphene, especially in electronics, one day replacing silicon. Other uses include being an antioxidant in paint, improving the lifetime of batteries, improving the efficiency of solar cells, and applicability in many fields under medicine, including biosensors, which I will be discussing about. So, what are biosensors? They are sensors that incorporate biomolecules as the receptors. They are made to not only detect other biomolecules such as proteins, carbohydrates, and metabolites, but also other bioactives like air pollutants and heavy metals. They must also be able to read concentration if deemed necessary, which they usually are. An example of a non-concentration dependent biosensor is the pregnancy test strip. An example of one that is concentration dependent is the blood glucose monitor. Now, a block diagram of biosensing is shown in the schematic. The receptors interact with the analyte and undergo a physical change. They are coupled with a transducer, which interprets the change as a signal, usually either electrical or optical. The signals are then amplified, processed, and digitally displayed for you to read. In the case of graphene, it is a natural choice for use as a transducer due to its high electrical conductivity and low sound-to-noise ratio. An example below shows a graphene biosensor designed by Chu et al., which graphene can relay three types of signals: optical, mechanical, and electrical. Now, for the workings behind the graphene biosensors, the specific device I will be looking more into is the graphene field effect transistor or GFET, which interprets the change from receptors as electrical signals. Graphene used alone is sensitive, however not selective enough, which is why in electronics, graphene has to be alloyed because of its lack of band gap. Being too conductive poses problems on control over the electrical current. As biosensors, graphene is functionalized with biomolecules for two reasons. First, the attached receptor carries some resistance, which can lower the conductivity and sensitivity of graphene. And second, with knowledge of the analyte being detected, a careful choice of functionalized biomolecules can be assigned to specifically target the analyte via the lock and key mechanism, imparting increased selectivity. The GFET device uses this functionalized graphene as the receptor and transducer. The graphene channel is attached to an insulating plate and a closed circuit is constructed around it. A voltmeter and ammeter are incorporated into the circuit to measure potential difference and current respectively. When the analytes come into contact with the receptors, they also carry a certain resistance that gets incorporated into the circuit. This is registered as a change in potential and current, which are read by the detectors. A study by Salzgeber et al. Demonstrates the process where they detect proteins by observing the device's voltage and current over time. A change in the graph corresponds to detection of the analyte, and intensity of the signal corresponds to concentration of the analytes in the sample. With this graphene technology, biosensors now have improved sensitivity and detection time. A known example is the use of GFET for early detection of cancer, which has better sensitivity and faster detection when compared to the traditional ELISA. Although, the main problem with graphene biosensors and graphene in general is that graphene cannot be commercialized as it is still unable to be industrially mass-produced. For those interested in graphene studies, the European Union is funding a 10-year graphene project worth €1.35 billion to find cheaper ways on how to synthesize or extract graphene, as well as finding other applications of graphene such as touchscreen devices and flexible electronics. Graphene biosensors is still a field waiting to be explored further. To end the discussion, I would like to present a Chinese patent entitled Three-Dimensional Graphene with Functionalized Amino Biosensor Preparation Methods and Applications. Although the main purpose of the invention is as a heavy metals biosensor, a secondary functionality was added to repair broken DNA. Biosensors are now being upgraded to have more than one function to lessen cost and to improve efficiency, and there are many synergistic combinations waiting to be discovered. With that, I end my talk. Thank you all for listening and have a good day.